Before leaving Chapter 3, I add new material that's not in the book, that is a alternative to cubic splines for drawing and generating smooth curves. These may be used in the next homework assignment that you're going to do that involves smooth curve generation. Bezier curves, notice the name Bezier, it's a French name, are alternatives to splines, and they're basically what we call parametric curves. Those in computer graphics are very familiar with Bezier curves, and this material might spur some interest in you to consider taking computer graphics, which does involve mathematics. It's usually involved in using different functions that enable one to generate the kinds of smooth curves that are needed for different types of image creation problems. The advantage of these Bezier curves is that they can be scaled indefinitely. In other words, that you can adapt this approach for higher and higher dimensions, from 2D to 3D to 4D to 5D and so forth, which are very useful. Of course, in graphics, usually you're just going to 3 dimensions at the most. Combinations of linked Bezier curves are called paths, and they're very easy to manipulate and actually can be used in animation as a tool to control the motion. And we'll see how that's possible in the next couple of slides. The lecture notes for this material have been deposited in Blackboard as an addendum to the Chapter 3 notes that you already have. So all of these notes are now available on Blackboard as well. Bezier curves can be thought of as applied in the time domain in the sense that they could be used to specify the velocity over time of an object, such as moving from one particular point A to another point B, rather than simply moving a fixed number of pixels per step. So it's a technique that can be used in computer graphics to control the motion of an object. The mathematical basis for Bezier curves is applications of what is called the Bernstein polynomial, which was defined as early as 1912. But it was the French engineer Pierre Bezier who demonstrated the use of these Bernstein polynomials in the design of automobile bodies, in terms of automobile design. And he worked for the French, he was contracted by the French automaker Renault, and this dates to around 1962. So, as I mentioned before, a couple of applications that you might find interesting. Definitely for computer graphics, drawing smooth curves, and we'll see how that's done in just a minute. Quadratic and cubic Bezier curves are the most common. Of course, again, related to computer graphics, we're not going to go above 3 dimensions, so cubic makes sense. Some very common computer software that you have used perhaps actually employ them. Adobe Illustrator's one, CorelDRAW, Inkscape, and even Microsoft Excel. There's a smooth curve feature for charts, if you're familiar with that feature. Is based on the use of Bezier curves. Adobe Flash and Synfig are 2 applications of the animation for outlining movement, which is done using Bezier curves. And many fonts are actually based on the generation of smooth curves with Bezier curves. So TrueType fonts are actually built from quadratic Bezier curves. And there are different font engines, for example, FreeType, that use them to generate such fonts. So we're going to look at what exactly do we mean by Bezier curve, and we'll start off with a linear Bezier curve. I'm going to do the mathematical constructions first, and then you'll see some examples that are illustrated that'll make it a little bit clearer. So a Bezier curve is defined by a set of control points. So whereas cubic splines, remember, smoothness is based on the continuity of derivatives through these piecewise cubic polynomials. Bezier curve is based on the idea of using control points to control the smoothness. So the number of control points, index 0, P0 through Pn, where n is called the order of the Bezier curve. So in other words, you have one more control point than the order of the Bezier curve. For a linear Bezier curve, n is equal to 1, which means you would have 2 control points. For a quadratic Bezier curve, n would be equal to 2, which means that you would have 3 control points. So by definition, the first and the last control points are always the endpoints of the curve. excuse me, are always the endpoints of the curve that you're interested in generating. And so that the intermediate control points usually do not lie on the curve. So this is not, it's not like interpolation at all. And so what we're talking about is, if I'm just drawing a little illustration here, that again you would have different points here representing control. And so if this was the x-coordinate of the first control point and this is the x-coordinate of the last one, your goal might be to generate a curve that looks something like this. And so the other control points are picked to sort of force the curve to turn in ways that you want it to. So the interior points, the interior control points, aren't really interpolated to. They're used again to control the oscillation or the rotation through from the beginning control point to the end. So for the case that is n is equal to 1, which is a linear Bezier curve, and you have the 2 control points P0 and P1, this is essentially mathematically what the Bezier curve looks like. And we said it's a parametric curve. Well, the parameter here is t. And the idea that a parametric curve is that this parameter would vary continuously from, say, 0 to 1. And as it varies from 0 to 1, it generates a Bezier curve. In this case, this would be a straight line, right? And so you can, if you look at the form here, as we've reduced it here to be of this form, 1 minus t p0 plus t times p1, so that you can quickly see that if you were to plug in 0 into the Bezier curve and then look at the final description of it here on the end here, then basically you're going to get P0 back, which means that's where you would start. And then if you were to plug in 1, so the parameter t again moves from 0 to 1, and by the time it had got to 1, you can see this term will go away, you'll get P1. So it's a way of specifying a line that's going to run from P0 to P1. Okay? That would be a linear Bezier curve. That's not going to be fairly useful for the application we're going to do for your next homework assignment. Quadratic and cubics will be more useful. So a quadratic Bezier curve, again, is this idea of a parametric curve based on this parameter t from 0 to 1, but now it has this particular constructive form here. And what you can think about is what it does is it linearly interpolates the points that lie on all the linear Bezier curves defined from P0 to P1 and all the linear Bezier curves that are defined from P1 and P2. So the construction of Bezier curves is very hierarchical in the sense that quadratic Bezier curves are based on linear combinations of linear Bezier curves. And I guess you could probably guess what's going to happen for cubic Bezier curves. They're going to be linear combinations of quadratic Bezier curves. So this is why it's a very, very simple and elegant mathematical construction of just using, this idea of taking linear combinations based on a parameter in a very structured way. If you take what I've indicated here for the quadratic Bezier curve and do a little algebra here, you can reconstruct it so that it looks like this. So this is a quadratic Bezier curve where when t runs from 0 to 1, again, you can check that if you were to plug in 0 for the Bezier curve, and notice the P2 term would go out, and you would have P1, and this term would be zeroed out because of the t. Again, it will do what you expect. It's going to start with the first control point, and then by the time t gets to 1, in this case, when t gets to 1, this term will go out, this term will go out, and all you're going to be left with is 1 squared P2. So again, there are 3 control points, and the first and the last one, all right, define the endpoints of the curve you're trying to generate. All right. So again, it's tracing the linear Bezier curve starting at P0, sort of in the direction of P1. So again, it's using the interior points to control sort of the direction that the curve, the ultimate b of t is going to take. And then by the time it gets to P2, it's going to roll from linear Bezier curves and starting with P0 in the direction of P1, and then to end up with linear Bezier curves P1 in the direction of P2. Again, we'll see a diagram of this in a second and make it a little bit more clear. So if you, again, look at the specification of the quadratic Bezier curve that we just had, if you were to compute the derivative, which would be very simple to do with respect to t, this is the particular form that you would get. That's the equation of the first derivative of a quadratic Bezier curve. So it can be shown that the tangents to this Bezier curve b of t, the tangents at P0 and P2 will intersect at P1. Okay. I can actually show that. So again, what this means is that as the t increases from 0 to 1, the curve starts off with a linear Bezier curve from P0 in the direction of P1, and then bends to arrive at P2, in the direction of P1. Now if we move on to finally the cubic Bezier curve, you can, again, the idea is that it would be a linear combination of quadratic Bezier curves. Now you have 4 control points, and remember that if these are the 4 control points, this is where the curve starts, this is where the curve ends. And so what we're looking at is how do we look at combinations of the first 3 for a quadratic Bezier curve, and then the last 3 for another quadratic Bezier curve. All right, and we just switch from moving from one quadratic Bezier curve into the second one, again, to control smoothness. So again, the curve starts at P0 going towards the direction of P1 and later arrives at P3 from the direction of P2. All right? And again, the curve typically does not pass through the intermediate control points. They are simply used to direct the curve. And again, we'll show you an animation which makes this very, very clear. So the reason they're control points is that the distance between your interior control points, especially to the endpoints, like the distance between P0 and P1, will determine how long the Bezier curve moves into the direction of P2 before it turns toward P3. All right. So you'll get to skew this curve so that it is sort of has a long tail in one direction or another, instead of being very symmetric and almost, and even on both sides. This is mathematically what the cubic looks like. And again, if you were to plug in 0 into this cubic Bezier curve, out would come, oops, here we go again, out would come P0. And if you were to plug in 1, by the time t gets to 1, you can bet you should be getting, it's going to knock out all these other terms because they involve a 1 minus t to a certain power. It's going to give you P3. So it's a way of tracing from P0 to P3 in certain directions using, again, a linear combination of quadratic Bezier curves. So Wikipedia has a really nice illustration of this, and I want to show these to you because I think you'll find them very, very useful to understand it. So what I've got are two illustrations of a quadratic Bezier curve and an illustration of a cubic Bezier curve. Since I'm using Acrobat to show this, I'll have to switch back over to PowerPoint to show you the animation. So in this diagram, we have these. The first image for each of the types are static, and this over here is these two are actually the animations. And I'm going to show that to you in a second, but I'll have to do it with PowerPoint. Not going to be able to see it as a static image in the PDF file. But over here, what you've got illustrated here is a quadratic Bezier curve. And again, you should have quadratic, you have 3 control points, and they're indicated here. Here's P0 right here. P2 is right here. And here's that interior control point, P1. All right. So the goal is your goal is trying to draw a certain kind of smooth curve from P0 to P2 using P1 to specify its direction. So again, what we meant before is a quadratic Bezier curve is a linear combination of 2 linear Bezier curves. And what's illustrated in the static image is the point at which your parameter is t is equal to 1 over 4, 1/4 to 0.25. Remember, t is running between 0 and 1. Okay? So when t is at 0, you're at P0, and by the time t gets to 1, you should be at P3. And so as t moves from 0 to 1, you are tracing out this red curve here. How is it doing that? Well, what we're showing at time t.25 is the linear Bezier curve, right? That initially started at P0 in the direction of P1, and then shifts and moves accordingly so that it lies on this line segment you can see here, going from P0 to P1, and this endpoint of the Bezier curve lies on the line segment P1, P2. So you can imagine as you move this point up this, and then remain tangent, that's what I should have said. So this line segment here that lives on this straight line from P0 to P1, and this endpoint that lives on P1 to P2 is always tangent, all right, to this red curve. So as you move the t, if you slide t here, what's going to happen is this endpoint is going to slide up here, while this endpoint is going to slide down there, and that process is going to generate this red curve. And what's cool is that you can then simply move this P1 point as you want to the right or to the left or up and down, and change the curvature. It's very, very interesting. I'm going to go ahead and then point out the cubic case before we see the animations. The only difference here is that where you have 3 control points for the quadratic Bezier curve, you've got 4 here. And this is a little more complicated because now what you're doing is you're switching from, you're doing a linear combination of 2 quadratic Bezier curves, and what we're showing is, again, this is a curve starting at P0, now ends at P3 because it's cubic. And what we're illustrating here is the position that you're at on the curve, all right, for a quadratic Bezier curve, which again is a linear combination of two. The quadratic Bezier curve is a linear combination of two linear Bezier curves. So what we have here is this line segment from P0 to P1, another line segment between P1 and P2, and another line segment from P2 and P3. And so this line that's tangent here at the point B there, which corresponds to T equals a point 25. So this is the Bezier curve, so we're illustrating there. As this point moves along the red curve, what you're doing is this tangent line is moving, right? It's going to flip over. It's going to start off being, in the direction of P2, and then it's going to flip over into the direction of P3 eventually, right? So again, these line segments here are sort of a border. It's like a bounding box, you can imagine. And so the line segments here this one has to start at P0 in the direction of P1, and then let me say it again. For this line segment, it has to lie on P0 to P1. This endpoint has to lie on P1 to P2. This other line segment has to be on this line from P1 to P2, and then its other endpoint has to be on this line segment, right? And so what we're looking at now is this tangent line has to move its endpoint on these other interior lines there. So it might be complicated to illustrate it without animating, so let me bring up the PowerPoint file that illustrates how the animation really works. So now I'm in PowerPoint and I'm going to illustrate these animations for you. So this is the illustration here. At the top, let's look on the right here for both of these. Again, the static image over here was just showing you when t is 0.25, running from 0 to 1, the particular point you'd be on this formally called Bernstein polynomial, which we're calling a Bezier curve. See what happens over here. When you start off, it's basically equivalent to this line segment P0, P1, and then the endpoint is moving, as you can see, always maintaining a tangent to the curve. So it's each time this point here is always the tangent to the line segment that starts off being completely on this segment. Again, the endpoint completely on this line segment here, and then eventually will end up at P1. So when the right endpoint ends up at P1, the left endpoint is at P1, the right endpoint is at P2, right? And so again, the position of this P1 is going to control the bending of this curve, whether it's bent more to the left or it's bent more to the right. So you can just simply move this control point to get the kind of curvature that you want. Okay, so it doesn't need the continuity of derivatives that we had before. It's just simply this sort of bounding constraints of these linear segments here. The cubic works very much in the same way, except that you have to have more control points to specify the switching from one quadratic Bezier curve to the other. So it starts off being controlled by a Bezier curve using P0, P1, and P2, and then it ends up being defined by a Bezier curve based on P1, P2, and P3. Right? Again, because the quadratic Bezier curve itself is a combination of two linears, and that's why you see these two green lines here. And you could imagine a fourth degree Bezier curve, you would have another control point, and you're going to add another line segment in there to control it. But again, you can see the difference in the bending of the quadratic here versus the cubic. And again, if you move the P1 and P2 appropriately, these interior points, you will get this thing to bend. You can squash it a little bit. You can make it higher. You can make it bend a little to the left or more to the right. So very, very nice way of getting a certain kind of smoothness that you want in computer graphics. So fortunately, Python, and especially in the Matplotlib library has a patch function that will accomplish the construction of the Bezier curve for you. It uses a particular object form called path to generate them, and it uses what are known as standard curve commands. And I'm going to provide you a Python file, which I have on Blackboard for you to use. You'll find you may or may not want to use Bezier curves for your next homework assignment, but it's an option. The curve commands are very simple. They're either move to a point, generate a line to it, or close a polynomial. And you'll see an example of this in the Python script file I'm going to give you. Typically, a path is defined as indicated here that you have vertices. In this case, it'll be the ordered pairs in a in a 2D Cartesian coordinate system, and then the codes. The codes are what these commands are specified when you move from one of your control points to another. So again, verts, in this case VRTS, is a list of 2D data points, and codes is a list of curve commands. And again, I've created a script file for you based on examples you can find online called Bezier.py that is an illustration of how you could generate a cubic Bezier curve using the patch function available from Matplotlib. So let's take a quick look at this Bezier.py file that is available in the source code section of the 370-377 Blackboard site. This again is a demonstration of Bezier curves. You would have to import Matplotlib, and this is just indicating how other particular modules it's using, importing matplotlib.path, importing it as importing the path object, PATH, capital with a capital P, and importing the patches function. So, which again, everything, a path is based again on a list of vertices and the codes that go with it. And so what I'm illustrating here is we're doing a cubic, right? So that's 4 control points. So this is just comments here to indicate this would be, the first one would be P0, P1, P2, P3. So we are drawing a curve from position 0, 0, say the origin, to the point x coordinate point 8 to 0. So we're going to sort of, you can imagine we're starting at the origin, going up, and then coming back down, all right? Like half a hemisphere or something like that. But this is going to be a cubic, so it's going to have sort of a cubic type of curvature to it. Then you specify the codes using this path object. So the codes would be from the path object, move to, and then there are other options which are all available online when you go to the Matplotlib page on the web. And by the way, I have put some references on Blackboard for web links to the Matplotlib library, so that but you can easily find it on the web through Google. But so these are options to how to move from one point to another. In other words, in case the first point, you're going to move away from P0 towards P1, and then from P1 to P2 be generating a Bezier curve, and another curve to get to P3. So, or what I should have said is that the other points are determined by the Bezier curve that's being constructed, and you're moving away from P0, and that specifies move to. So you can look at the specification of what those different commands mean. Most of the time you'll use something like this, move to followed by a set of curve4 commands to generate it. But you can look online to see the differences in the commands. I believe there's like curve4 and curve3, but curve4 is a cubic. We're specifying a curve with 4 control points, and that's why it's called curve4. If it was a curve3, then it would be drawing a quadratic Bezier curve, because it's based on 3 control points. Okay. And this is an illustration of, again, how to plot it. and how to get some particular color options and so forth. And then we're going to generate take the path and generate a patch, and the patch will be the tracing of the Bezier curve based on that path. And then we got putting some text in on the plot just so we can see sort of where these control points are. Okay. And again, in this file to help you, just so that if you didn't want to go looking on the web, here are some of the path codes: stop, move to. Again, move to in this case means pick up the pen and move to the given vertex. Curve 3 generates a quadratic Bezier curve. Curve 4 generates a cubic. And closed poly draws a line segment to the start of the current polyline. All right. So these are the meanings of those curve commands. So if we simply run it, again, running it directly as a from specify the file name, because the Python path is at the beginning of the script. We run this, running this locally, and there it generates. Again, we are constructing a Bezier curve from P0 going to P3, and then we use these points here to sort of control how it bends. All right? And so again, just moving the P1 and P2 would generate a different kind of look. And again, very, very useful in computer graphics. It's an alternative to cubic splines. Sometimes you'll notice when you're connecting cubic splines, there's sometimes some rough edges. It's hard to get some of the splines to get smooth, certain abrupt changes in a curve. And this is a really nice alternative sometimes to get that smoothness in a very continuous way.